working on. Is this visible? Ozonolysis.
Yes, sir.
Right. So I was talking about the synthesis, how primary ozonide is synthesized. Then primary ozonide due to steric repulsion, due to lone pair repulsion of these three oxygen, three non-bonding electron pairs are present on these oxygen, which repel each other, making them unstable. That's why this ring cleave and result in the formation of this entity. Now, this molecule undergo another addition, but the very first is a thin addition. You see, both oxygen, this oxygen and that oxygen, they are added at the same time. They are not added at a different time. This is a concerted mechanism. New bond formation and old bond dissociation is taking place simultaneously. So this is resulting in the formation of primary ozonide. With under steric hindrance, it regenerates into this aldehyde and this entity. You see, this is also aldehyde, but this is oxidized aldehyde, which is unstable as well. What happens? You see, this is a carbonyl type addition. You have already come across another type of the addition. If I switch back to earlier, this one, carbon oxygen or carbon nitrogen, carbon sulfur double bond, and nucleophile can approach this. So if you look at in this case, we have a electron deficient center, carbon oxygen double bond. We have a nucleophile present in the molecule. So this oxygen donates electronic density to this carbonyl carbon. This carbonyl donates this electronic density here to this carbon, which is electron deficient, and this electron pair transfers on oxygen. In fact, this bond is the driving force, because oxygen making three bond positively charged intolerable according to rules of presence. That's why it takes this electron pair off. This olefin, this ketonic system donates this electron pair here. This carbon become electron deficient, so this oxygen donates this electron pair here, and it results in the formation of this entity. Now look at the difference. What is the difference here between this carbon and that carbon? In the very first step, there are two double bonds. One is sigma, other is pi. In first syn addition, what is happening? We get a pi bond broken, right? So pi bond has been broken in the very first step. What happened in the second step? In next step, here you can see this second carbon single bond. You see, this is also broken. So we don't have this carbon and this carbon connected with each other. They are broken. So in first syn addition, we are getting this pi bond broken between carbon and carbon. In second step, it is a rearrangement due to repulsive forces, so generating cleaving the other sigma bond between two carbons of the olefin. Now you see here, this carbon and that carbon, they are not bonded. There are three oxygens in between, but all oxygens are not connected to each other. Just focus on the structure of primary ozonide and the secondary ozonide. You can see both of these are three oxygen consecutive, two oxygens are consecutive, and one is different. So this is called secondary ozonide. I have made a difference. There is a methyl here. There should be a carbon here, but I deliberately made two carbons here just to understand you some aspects here. So let's see if we have a methyl present here, one hydrogen. Another carbon, we have both alkyl groups, maybe methyls. Let's see. So this secondary ozonide is a stable entity. This is a heterocyclic entity, heterocyclic compound. If we react this with some entities, we can convert that into very interesting components. For example, if we react this with zinc metal in the presence of acetic acid. So what is this? Zinc in the presence of acetic acid. It reacts with each other. So zinc reacts with acetic acid to form zinc acetate and atomic hydrogen. When this atomic hydrogen adds to this, so atomic hydrogen is a common, you have studied this in earlier classes, nascent hydrogen. which is in fact atomic hydrogen. So that shall react with this and it shall reduce this entity. It shall reduce that, let's say this electron pair transfers here. So we get a carbon oxygen double bond, and similarly it shall get this electron transfers there. So this shall be forming a water and oxygen molecule. So in fact, we shall get a aldehyde or a ketone. This is when we are using a reducing agent, atomic hydrogen. So we get aldehydes or ketones. It is not further oxidized or it is not further reduced. If these are produced, so atomic hydrogen is still present, but it doesn't reduce aldehyde or a ketone. It only reduces high uh, reactive intermediate secondary ozonides. Or instead of these, we also have dimethyl sulfide. If we have a sulfur entity, on both sides we are have methyl, just like dimethyl ether. If we have a thioether, means sulfur bonded with both sides methyl group. This is called dimethyl sulfide. If we are using the same, it also results the same results. So we get a aldehyde and a ketone. Let's say we also have another methyl group here, so we shall get only ketone. If we have uh, only one carbon present here, not two carbons, so we shall get two aldehydes. If these two alkyl groups are same, so we get only one kind of aldehyde. Secondly, if we are reacting this with another reducing agent, sodium borohydride. Borohydride is a hydride transfer. It transfer H negative. Pattern is different. So whenever we are having this hydride transfer, hydride shall transfer this, and it shall not only first reduce this to aldehyde and ketone, it shall further reduce, because hydrides are reactive towards aldehyde and ketone. First, it shall also form the same product, but sodium borohydride shall not stop here. It shall further reduce these carbon oxygen double bonds and converting them into secondary alcohol and primary alcohol. This is what happening, difference between the two reducing agent I have highlighted here. Similarly, let's see if we are going for this entity, hydrogen peroxide. This is not a reducing agent. This is an oxidizing agent. These two are reducing agent. One is a mild reducing agent, other is a strong reducing agent. Mild reducing agent generates only aldehyde and ketone. It further doesn't react with this. Sodium borohydride not only react with this, but the first these two products are formed, it further reacts with them and convert them into alcohol, more reduced form, highest reduced form. Hydrogen peroxide is an oxidizing agent. It oxidizes this entity and results in what? It results in a ketone, no doubt like this, and it results in aldehyde. Aldehyde in the presence of hydrogen peroxide further oxidized to acetic acid. So this is the difference. Look at this one and that one. Here we get ketone and aldehyde. Here we get ketone and carboxylic acid. And here we get only alcohols. If same secondary ozonide is reacted with ammonia, it results in the formation of a carbon nitrogen bond followed by hydrogenation. Uh, so ammonia first adds, so it results because when it is adding to this, so it is resulting primary and secondary. This is a amine, this is another amine. So both of these are primary amines. So this is what is going on when we are quenching the secondary ozonide under different conditions. Same, first step is same. We can react. In fact, you doesn't know how we can generate ozone. Ozone can be generated. If you have experience, just if I present you, not only this is the one procedure that molecular oxygen converts into ozone at in the presence of high frequency radiation. You can also observe yourself. You would have come across, let's say, those people who have visited a grid, electric grid station, or you are working near to a machine which have a very high electric potential it needs. just like lathe machine or any other machines, if working closer to that, you would have smell a specific fragrance there. Or if you have reached very close to a transformer, electric transformers, so you have smell a garlic type fragrance. This fragrance is in fact due to ozone. Due to electric discharge, ozone is also synthesized. For example, when in the clouds, electric discharge takes place due to this lightning, which is also very high radiations. So that also generates, converts molecular oxygen into ozone. At the same time, when we are having ozone is formed by this method. So in fact, air contains, if you remember, 20.99% or almost 21% oxygen in the air. So when a high electric potential is available to an instrument, so in due to this high electric potential, it produces some ozone. So this garlic type small fragrance, very not unpleasant. So this fragrance near such instruments which is using ultra high uh, electric potential they are using. So if you visit a grid, you shall definitely where there are different electric supplies are coming 22 kV kilovolt energy is been coming through the wires. So they are producing this smell. That smell is that of ozone. This is how ozone. But how we produce this? We pass the ozone layer through an instrument. This instrument is nothing. It has attached with a high electric potential. So when oxygen, molecular oxygen passes through this, it converts into oxygen. But only very few percentage of this molecular oxygen converts into ozone. Just 0.4 to 1% molecule. Let's say if 100 molecules are passing, so maybe one molecule is being converted into ozone. So what we perform is this ozone is bubbled through the this olefin solution. This olefin is taken in an organic solvent and ozone is bubbled through. So very less is present. So this one, it is highly unstable. It is a strong oxidizing agent. Once it is present, it instantly reacts with this carbon-carbon double bond. So this is how ozone is synthesized in the laboratory. But on large scale, it is a nature which produces ozone. Ozone by the reaction of molecular oxygen with atomic oxygen. How atomic oxygen is generated? By the cleavage of oxygen-oxygen double bond. So this is what photolysis means. The high frequency radiation coming from the sun cause this for us, which is a protective layer. It filters the high frequency radiation, not 100%, but mostly 90 to 95%, because very small UV radiation approach over Earth. And this UV radiation which are approaching to us, it is also very useful because vitamin D is synthesized by this. If no UV radiation is coming down, then there shall be a very poor uh, percentage of the UV, and we shall not be able to synthesize vitamin D ourselves. These days, when the pollution is going, level of pollution is decreased to small extent due to lockdown in most of the countries. So the ozone layer has been rehabilitated. So it has been increased and in a very healthy atmosphere at the moment. Earlier, many vehicles and many other industries which are producing free radicals that affect this ozone layer, in fact. So that's why these, especially CFCs, you have come across chlorofluorocarbons. These are very dangerous for ozone layer. They, in fact, generates free radicals. These free radicals damage the ozone layer. So they are very toxic, and the depletion in ozone was observed. But these days, for almost a month or 3 weeks past, in which this ozone layer is replicating, it is increasing. So it is getting much better for us. It is filtering now the toxic radiation. So anyhow, this is the ozonolysis. Ozonolysis is very useful. It is a thin addition, but thin a product which result is not stable. It results in the formation of these two units, which further undergo form secondary ozonide, and secondary ozonide we can quench with a different reagents to form a variety of different compounds. Likewise, I have highlighted. The other one I'm interested in to present is the hydroboration. Hydroboration is also a syn addition. What is hydroboration? The word presents addition of hydrogen and boron. If you remember how boron exists, next slide I have presented. If you remember, boron belongs to group number 3, and group number 3 is boron family. Boron, aluminum, gallium, indium, thallium, etc. So this boron is electron deficient. Why? Why we call it electron deficient? Just look at this electronic configuration. It has 3 electrons in the valence shell, 2 in second s, and uh, one in the p, 2p. So it hybridizes, forming sp2 hybridization, and boron makes 3 bonds with the covalent bond with the other. So how many electrons it shall have? If it is making 3 covalent bonds, it has only 6 electrons in the valence shell. So according to octet rule, there should be 8 electrons for a stable entity, but it contains 6. That's why it is electron deficient. So it rapidly reacts with any entity which is nucleophilic, which have a non-bonding electron pair available. It instantly react with this, fastly reacted with it. So this is the what boranes are. I have highlighted this here. Next slide, you can see this is borane, B2H6. Binary compound of boron and hydrogen is called BH3. This is I have present one boron, 3 hydrogen it is bonded. One boron bonded with 3 hydrogens. But what happens that boron BH3 doesn't exist independently because this is unstable. This is very similar. You have already come across about the halogens. Halogens exist in the form of Cl2, Br2, I2, not in chlorine, bromine, iodine, atomic state. Very similar, oxygen, nitrogen, and many other gases doesn't exist in this form. So they exist in dimeric form. So BH3 also exists in dimeric form. How? So this hydrogen of the boron, this is electron deficient. It makes a bond with boron which is more electronegative than this one. So in fact here, this is donating partial electronic density just like hydrogen bonding. And the one of this is making a bond with the other boron. So this is in fact, you can observe in this case, this is a small hydrogen tie bonding which makes this formula B2H6. So borane exists in dimeric form in fact. But I have presented just for clarity. It is the Hb bond R2. Although it doesn't exist, but I have presented this in a monoatomic state. But it exists in dimeric form in fact. What happened in hydroboration? Let's see if these two bonds, I have presented all 4 bonds here, mean alkyl groups are attached. If let's say there is 2 alkyl group present here and 1 group is present here, then boron shall always prefer to add to such site which is sterically less crowded. Hydrogen, smaller in size, shall go to the sterically more crowded site. So this hydrogen boron bond is breaking, and a pi bond between the 2 carbon is breaking. These are the 2 bonds breaking, and 2 new bonds are forming between olefinic carbon and this hydrogen, between olefinic carbon and boron. These are the 2 new bonds forming. What transition state? If you remember, transition state is always involved. This is a transition state I have presented. Carbon hydrogen bond, half bond, carbon bromine, half bond. The bond presented in green color, these are the new bonds going to be formed. And 2 bonds I have presented, pi bond here between carbon carbon, and a sigma bond between hydrogen and boron. Both of these are cleaving, but they are also dotted, mean they are half bond as well. So this is the transition state. What happens further? Hydrogen and boron. Just look at here. Both hydrogen and boron are added above the plane. In another, both of these hydrogen and boron shall be added behind the plane. So two new symmetric centers are generated. Four isomers are possible, but two of them are forming. This is one I have presented. The second one shall be in which hydrogen and boron shall both shall be behind the plane. But you shall not get any isomer in which both of these are opposite, hydrogen and boron opposite. You shall not get any because this is always following a syn addition. Now, let's see, I have presented here an example. If two alkyl groups are attached to boron and one hydrogen bond only, so you see we have increased steric crowding around boron. And you see this olefin is tri-substituted, one methyl, one alkyl group, one alkyl group. So this is more sterically hindered and this carbon is sterically less hindered. So boron shall be added to sterically less crowded and hydrogen shall be added to sterically more crowded. So in this case, when hydrogen is adding here, boron is adding here. Now again, there are two possibilities. They can add above the plane, they can add behind the plane. So two surfaces this olefin have. So both hydrogen and boron can add above the plane, which is presented in structure number 3. Boron is added above the plane, hydrogen is added above the plane. So methyl shall go behind the plane. If this is approaching behind the plane, so boron shall be bonded behind the plane, hydrogen shall be bonded behind the plane, so methyl shall go above the plane. So this is two possibilities only. It can add above or behind, resulting in the formation of compound number 3 and compound number 4. Both of them shall be formed. You see, both of them are enantiomer. It is having boron below the plane, it has above the plane. It has methyl behind the plane, it has methyl above the plane. Totally opposite absolute configuration. So these two entities are in fact stereoisomers. They are enantiomers of each, but both of them are forming in exactly 1:1 ratio. So the reaction is not stereo selective, but it is stereo specific. Because out of 4 isomers, 2 isomers are formed. Two other are not forming at all. So this is a stereo specific, but it is not stereo selective because the both isomers which are resulting are in equal ratio. This is what we call is hydroboration. So hydroboration, these reagents which adds to this is entirely different. These are a few specific that I have highlighted in next slides. You can see this. So in this case, I have presented, this is our olefin B2H6. The structure of B2H6 you have already seen. This is a B2H6. These are the two hydrogens common between two BH3 entities which are coordinating with borons and resulting in this dimeric species. This is called B2H6. B2H6 adds across this. Boron shall add to sterically less crowded. Hydrogen shall add to sterically more crowded site. So one addition takes place and we get a boron bonded with carbon, which is this side, and hydrogen is added to this carbon. Again, we have two hydrogens with boron. It shall again add to another entity. Boron shall go to sterically less crowded site and hydrogen shall go to this one. So in fact, two molecules of this react with one BH3 unit to result in the formation of this entity. We have this carbon sterically less crowded of both olefin bonded with boron and hydrogens are added to these entities. No doubt this addition shall be a syn addition. We are not talking about stereochemically here. I am just going to present a variation in these entities. What this group is called? This group is commonly called as siamyl, 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 right? So two thiamyls are there. This is called disiamyl borane. Boron bonded with one hydrogen, right? It is abbreviated as SIA2. Di, 2 stands for di, SIA stands for thiamyl, and BH stands for borane. This is called disiamyl borane, abbreviated with this, right? So this is used as a hydroborating agent. hydrogen shall add to sterically more crowded and boron shall add to sterically less crowded. If we are using BH3, then the steric hindrance between boron and hydrogen is not very high. It is not very different from each other. That's why we have replaced that. So we are making some sterically crowded terminals. Now this boron, one side is hydrogen, other side is a big group. You see these two big groups are there. So which it shall not let to add to a sterically crowded terminal site. Let's see if we start with an olefin which have 4 methyls. All no, this olefin is equal because this carbon and this carbon have same steric hindrance. That's why either boron add to this side or it add to this side, it shall be not making any difference. So boron add to one side only. Either it is this one or it is the other one. One side hydrogen, other side is boron. So this is different. You see, these are two methyl groups. Now it is making this as BH2 sterically too much hinder. This carbon is a tertiary carbon, if you remember. Carbon 1, 2, 3 carbon it is attached with. This carbon was a secondary carbon, 1 carbon, 2 carbon. It is not sterically much crowded, but this is asterically much crowded here. This is sterically too much crowded. So that's why it shall not add to another olefin. Very similar to dicyamyl borane. It exists in this one. This group is in fact called hexyl. Hexyl. So that's why this is called hexyl borane. It is presented with THBH2. You see here there is a BH boron bonded with one hydrogen only because two successive additions has taken place. There is a not sterically much crowded, but here it is sterically highly crowded. That's why only one borane addition has taken place. This is called hexyl borane. These are not normally being used in synthetic chemistry, but one important aspect that we call 9BBN. This type of organoborane are exclusively used. What is this? So now how 9BBN can be synthesized? It is synthesized from this olefin. Look at this olefin. This is called 1,5-cod. This is abbreviated name, but 1,5-cod stands for what? 1,5-cod stands for 1,5-cyclooctadiene. 1 and 5 is showing its position. Let's say this numbering starts from here 1, 2, 3, 4, 5. So we have two double bond at 1 and 5 position. So this is 1, 5. What ring is this? This is a 8-membered ring, cyclic. So cyclooctadiene. So 1,5-cyclooctadiene, this is called 1,5-cod. This is abbreviated name. So this abbreviated name undergo addition to boranes. So boron when add first one, because you see this is a sterically less crowded side. Both carbons are equally sterically crowded, this side and the other side, and they are symmetrical. Either boron add to this one or this one, makes no difference. So boron adds to one side, let's say this side, hydrogen add to the other side. Now there are two possibilities. First, it is been added. Now we have BH2 remaining. So this BH2 can be added within the same ring. It can add to this carbon or it can add to this carbon. If boron added here adds to this one, so we shall get a 1, 2, 3, 4, 5, 6, 7-membered ring versus 5-membered ring. So 5-membered and 7-membered are unequal. But what happens if boron is present here? The boron add to the diagonal opposite side. This is the opposite side, this boron. Why? Because if it adds to this, we have 1, 2, 3, 4, 5, and 1 boron, 6-membered rings. And we shall have 6-membered ring other side. 2 6-membered rings shall be formed, which acquire a chair conformation. This is being presented here. You see, this is one chair conformation. Look at here. This is one chair conformation, boron is bonded. And this is another chair. You see, this one. This is another chair conformation. So there are two chairs present in this case. And boron is present on the top. This is a bicyclic system. And this molecule is also presented in this way. This is also the same presentation, just like you have come across how these rings are being presented. So this is the same presentation. This one and that one is same, but the angles are just different. Now you can see this is one chair conformation. This is another chair conformation. So both of these are in fact equal. They are same, but rather this structure is difficult to draw. So rather drawing this, we draw this in this way. This is a small crescent. A small crescent is what? It is showing boron is bonded. This is bonded one ring. This is another ring. So boron is bonded to two rings. It is the fact boron is bonded to this ring. Boron is also bonded to this ring as well. So 9BBN is presented with this one in synthetic chemistry. And why it is called 9BBN? 9BBN, this is called because it is the IUPAC name of them. How? Let's say whenever we are having a bicyclic system, we are numbering this. Either this carbon can be number one, this carbon can be number one. Numbering always starts from bridgehead carbon. Now either we are stating this numbering from this side or from this side. So both have equal number. We start the numbering from larger ring. So in all cases this is same, 6 member ring. So if let's say we start numbering from here, this is carbon number 1, this is 2, 3, 4, again this is bridgehead carbon number 5, this is 6, 7, 8, and this boron is number 9. So 9 position we have boron. This is called 9 bora, and it is having 2 rings. So bicyclo. You have seen this nomenclature of bicyclic system in previous semesters. So I hope so. This is repetition for all of you. So it is in parenthesis 331, stands for what? 3 atoms this side to the bridgehead. You see these are the 3 atoms. 3 other atoms are on the other side. So 3, 3, 1, 1 is above the plane between the bridgehead. This is how we can present this. And total 9 atoms are there, including boron. That's why this is called nonane. So we have 9 from here, B from here, B from here, and N from here. This is called 9BBN. Is it clear to everybody? Are you listening me?
Yes, sir.
All right. So just 5 minutes are remaining. I don't know why the 5 minutes are remaining. Is it clear?
Sir.
When we logged in, all right, we logged in at 37. All right, so we are short of time. In next slide, I shall just elaborate. This is the last slide I am interested in to present the molecular orbital approach to present this carbon-carbon double bond that I have presented here in this slide. What this slide is presenting, just focus here. This is the reaction you are studying at the moment. Olefin electrophile is adding to an olefin, resulting in the formation of products. It may be a syn addition, it may be a anti-addition, but adding entity is always electron addition. This is what you have seen. It may follow concerted mechanism or it may follow the stepwise mechanism. If it is concerted, it shall be syn addition. If it is stepwise, it shall always be a, in fact, stepwise shall be always a anti-addition. So
Entire.
if you remember, in this case, we are having a carbon-carbon double bond. Keeping in mind, we have a pi bond present here. So whenever a molecular orbital, pi bond is what? Pi bond is formed by the linear overlap. So it results in what? It results in the formation of an orbital which is lower in energy. Pi is a molecular orbital lower in energy, and pi star is a molecular orbital which is higher in energy. You are familiar with this terminology. Pi is lower in energy and pi star is higher in energy. This carbon contains 1 electron, this carbon contains 1 electron. Both electrons shall go when 2 orbitals are available according to Hund's rules. They shall go to lower energy with opposite spin. I have presented both of these electrons with opposite spin. So both electrons are present in pi and pi star is empty. This is what you can see. Now look at, I have presented the molecular orbital diagram of both pi and pi star. What pi is presenting, first look at here. This electrophile is electron deficient and our olefin is electron rich. But this pi bond have two orbitals. One is pi, other is pi star. Pi is occupied, have two electrons, pi star is empty. Now electrophile approach either pi orbital or it approach pi star. This is a question. This is important. Let's say if this electrophile is electron deficient, it has no electron in bonding, and pi star it is interacting with. Now look at pi star is empty. This is empty. When they shall interact with each other, what shall be formed? We shall have no electron. What shall be the bond order? Electron in bonding minus electron in anti-bonding divided by 2. This is a formula to calculate the bond order. So here 0 electron in bonding, 0 in non-bonding, 0 minus 0 by 2, answer 0. So it means if electrophile is approaching pi star, it shall be an insignificant molecular orbital. Why insignificant? Because it shall lead to a 0 bond order. This is interesting, right? Now focus on pi. Pi have 2 electron in the here. If this electrophile interacts with this, it has no electron and pi has 2 electron. Both electrons shall go to the bonding. Anti-bonding shall be empty. What shall be the bond order? 2 minus 0 by 2. So it shall be in fact 1. 1 shall be the bond order, right? So in this case, we are in fact having 2 bond orders. If it is interacting with pi star, it shall have 0 bond order. If it is interacting with pi, it shall have 1 bond order. So that's why it is going to interact with pi. Here I have presented the structure of the pi and pi star. Pi is resembling the these 2 orbital, mean this is the electronic density around carbon-carbon sigma bond is equally distributed. This is called banana shaped molecular orbital. This pi is having like that. It means it shows that electronic density is present maximum in between the orbital. Here maximum electronic density is available. Maximum electronic density is available. So electrophile shall not react with this pi star, where electronic density is maximum present at the center of molecule. It has 0 electronic density available, but here it has maximum electronic density. So that's why what we can conclude, we have just 1 minute remaining. I shall conclude this, that this is the diagram I have presented in larger size. Where the electrophile shall approach, it shall approach from this side or that side, because here maximum electronic density is available. And if you notice where this is approaching, if I intersect this carbon-carbon sigma bond, it is perpendicular to this, making a 90-degree angle. So it means electrophile shall approach perpendicular position from here to this carbon-carbon sigma bond. So this shall be disconnected in a few seconds.